All right. Hey everybody, welcome back to Together Time with Luke. It's Saturday morning, and today we're going to go through equalizers and compressors and how they relate to the broadcast industry and music as we know it today. We're going to talk about some famous compressors, some famous equalizers, some old mixing desks like the old consoles that you saw in studios back in the day. And before we get to all that, though, we have a correction to make, a very important correction. If you will remember back in our very first conversation about audio, in part one, the physics of sound, the first thing that I said to you, the very first thing, before we even ran the intro, I said, if a tree falls in the forest, does it make a sound? And then I said, no, of course it doesn't. That's a stupid question. Let's move on. But turns out, in moving on and doing a lot of the research here, I've come to learn that maybe it's not such a stupid question. So I'm going to explain to you why it's not a stupid question. But first, smoke if you got 'em. Let's take a look at the human ear, just for 1 second. Here's the human ear. Let's switch over to my desktop so you can see the human ear. Here we go. Going over to the desktop now. Here's the human ear. All right. So something makes a sound out in the world, and the sound waves bounce around, and they come into your ear here and funnel into this ear canal. The ear canal is it's almost the same size in everybody, so it's in a range of sound. And the interesting thing about the ear canal is as the sound moves through here, it makes a resonance, like a tone. If you were to cut this little piece out of a person and play it like a flute, it would play a single tone. And that tone would be somewhere around like 3 to 5K in the frequency range. Don't worry about that. I'm just telling you. So this is the way sound works. It comes into your ear, it funnels through this ear canal. Some resonances get added as it goes through your ear canal, just as a byproduct of moving through the space. Then here is your eardrum. So the sound hits that, it makes your eardrum vibrate, and that vibrates in this little chamber here, and it gets over to this situation that looks like a snail. This is called the cochlea. Inside your cochlea, there's a bunch of little hairs, like the cilia on a tomato plant or something like that. There's hairs inside this little tuba-shaped thing, and the sound waves excite those hairs. And what that does is send a signal to this yellow bit here. This is called the auditory nerve. And the auditory nerve takes that just like it was an audio cable right to your brain. And then your brain is what actually turns those vibrations and that signal into sound as we hear it. So the argument actually does stand. If the tree sounds, if it's an apocalyptic world, right? If there's nothing around still that has ears and a brain, and a tree falls, does it make a sound? I guess if there's no brain to interpret the sound, it does not make a sound. So I stand corrected. If we go back to our very first slide here, if a tree falls in the woods, what happens? I was wrong. So there, I said it. All right, now we can move on. So I wanted to also take a moment to recognize the references and the sources of this material, because obviously, I didn't use a lot of this old gear I'm talking about. I don't have history with it, but I've learned it from taking courses from other people and reading things and a lot of the manufacturers themselves. So here are my primary references for this information. First and foremost, I'm getting a lot of this information from Mixing with Mike. Michael White is a mixing engineer who is most notable for working with Whitney Houston. Who actually, if you go back to the Uncanny Valley podcast, the episode where we discuss people that are dead and alive, I learned that the Bodyguard song, I will always love, that's not even Whitney Houston's song. Anyway, but that has nothing to do with Michael White. Either way, this guy is the one that produced that song. And he does tutorials like this one and also private instruction, and I've paid for his courses and gone through them a lot of times. And I learned a lot about the analog gear and its history from him. So I'm taking a lot of that from this guy. So if you want to get into more detail about some of that old gear, like from somebody that's really used it and knows it well, his YouTube channel has a lot of free information, and his website, Mixing with the Mic, offers courses. So check that out. Also, I'm referencing another YouTuber here. The YouTube channel is called Technology Connections, and this guy's just a nerd that talks about electronics. So he goes into how valves work and how transistors work and how toasters work and just any kind of little electronic project. That's his deal. So I'm also going through a lot of his videos and mixing them together. Now, I get information about the gear itself from the manufacturers, and these are distributors of that gear. So Sweetwater Sound sells music gear, and they often have the manufacturers of these old products come and talk about the history and do workshops and stuff like that as sort of a pre-sales thing. So I've watched a lot of those. Vintage King, more so with the vintage stuff, obviously. Sound on Sound is a publication that does interviews with producers and musicians, and it's all about sound, and I get a lot of information from there. Obviously, Wikipedia. And then here at the bottom, this is Shooty School. This is my buddy Sean does a YouTube channel, and he does tutorials that are right now, I think, primarily focused around live sound, like ringing in a concert hall if you're doing a live sound type thing. So I got some information from there too. And he also goes into depth in drum programming and using Easy Drummer and gives jam tracks and stuff. So let's shout out Shooty School here. So if you're looking for more of this type of content, these are some good sources for it. Now, we're talking about equalizers and compressors today. You definitely know what an equalizer is. You've seen a million of them on devices your entire life. But compressors, maybe you don't see so much. That's okay. Neither one of them is a very complicated machine. So we're going to talk about the history of these, and I want to do that because when we talk about the earliest compressors and equalizers, they were just really simple. So it's easier to understand when you look back to before there was a million buttons, right? So let's talk about the early ones and how they evolved into what they are today and how we can use that knowledge to our advantage. Here's an important concept I want to talk about. I guess we're not through the sciencey bits quite yet. So a lot of this technology, as we've talked about before, was driven by the phone company and the broadcast industry. And the phone company figured out a way to send those carbon microphone signals over the phone line pretty well, but they were trying to find ways to cut costs even more. So what they did is they hired a couple of people to study the way that we perceive sound to see if any frequencies were more important to us than any other frequencies. So they hired a couple guys to do the research, and their names were Fletcher and Munson. And in 1933, this happened, and they learned that we don't hear sound in a linear way. Humans don't. This is called the Fletcher-Munson curve. So it states we don't hear all frequencies equally across the frequency spectrum at the same volume levels. Some frequencies stand out to us more than others. Now, just as a quick throwback, if you think about the human ear and what I said happens in this area, it kind of starts to make more sense, right? So let's take a look at this curve here. So Bell Labs sponsored this research, and they were just trying to figure out a way to make phone calls cheaper. That whole time, from the 30s up until like the 80s, they could have made phones sound fine, but they didn't because it was cheaper not to. So they just capitalized on that. So they measured it in 1933. And they found that same area in the ear canal, around 3.5K, that's where our ears are most sensitive to sound, because that little resonance hole amplifies that area a little bit. So it's really between 1 and 4K, but 3.5 is the average. And I think it also changes a little bit as we age, but I did not read that anywhere. I'm making it up in my brain. So all of our human languages are... they all start, the important bits of the language exist in this range. So it's the beginnings of our words, the transients, the s's. These all exist. The consonants, they all exist in this range that's easier for us to hear. So we can hear people speak far away, whereas music far away is kind of less intelligible. It can fade away in the background faster. These things stand out to us as important. So here, if you played your ear like a flute, it would make a 3.5 kilohertz tone. Another thing we're seeing here is that you never actually hear the low end and the high end at the same volume, at the same relative volume. And this is important as we work with audio and try to make critical changes, because what it means for us is that as we change the volume up and down, our perception of the low end changes with that. So you don't hear bass frequencies when the volume's low, but then when you turn it up, you can start to hear the kick drum more. That's because as you turn up the volume, this curve starts to flatten out a little more. Down here, it's tough to hear those low frequencies, but up here when it starts to get louder, that curve is, you still don't hear them great, even loud, but it's a lot smoother a curve here. And you can also see this little boost that's happening at 3.5K at different levels. It looks like that is more pronounced at lower volume levels than at higher volume levels. So when we listen to music louder, we think it sounds better, but what's actually happening is we're hearing it just more evenly. We're hearing the low end and the high end more evenly, and it sounds better. That's important for us to mix. So when we're mixing, we try to keep a volume and stay there, or just switch between a loud and a soft, but not always constantly fiddling with the volume. If you're doing that, then any change that you're making while you're fiddling with the volume is kind of irrelevant. So keep that in mind. That's the Fletcher-Munson curve and why it's important. So we hear all the frequencies across the spectrum better when they're about 90 decibels loud, when they're 90 dB above whatever. That's the SBL. This is why when you go to concerts and stuff, everything just sounds better. It sounds more full, it sounds more alive, it sounds more real. It's because we're hearing more of it. Now, equalizers. This is also kind of it started in the phone lines, but they were using physical electronic filters. So they were just cutting off the frequency spectrum at a certain point. So they could say, well, the human voice doesn't really start until somewhere around like maybe 120 hertz. So let's put in a physical block. So we're not even sending anything below 120 just gets cut off before it even goes out the line. So they were doing that sort of equalization with hardware things and filters. But the first kind of EQ as we know it came from Hollywood, and it was for balancing out theater for showing a film. And this is what it was. It was the Langevin Model EQ 251A. This is the first EQ that had the sliders, that was slider controlled like this. And it had two controls on it. You could set the low end to either 40 or 100, or you could set one of these 3K, 5K, I think that's 10K and 15K. So you had two controls and two sliders, and that was it. And that's all you could adjust. So when we talk about EQ, it's a tool to manipulate the frequency spectrum. So let's take a quick look at the frequency spectrum itself. I'm going to open up my DAW here, Studio One, and we'll just open up a software equalizer so we can just look at what it does. Do 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 do. We'll create a new song. Here we go. It's a new song, yeah. Do do do. We're gonna make a new track on that song, and we're gonna record this song. Do 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 do. I'm gonna sing into the microphone, and we're gonna record it, but it's not gonna work. Why? Probably because I'm sending the sound over to you. All right. So that didn't do what I wanted it to do. Never does in a live setting. Why? Why has it got to be like that? Why? Why? Here we go. Let's just fix that real quick. And then I'm going to sing another song for you, and we're going to record the signal into the sound software. It's going to be so cool. All right. So now we have our song here, and I'm going to create a loop around it so it just plays over and over. Lucky you. And we'll trim this up a little bit, and then let's throw an equalizer on it. I'm just going to, don't worry about what EQ I use. I'm going to use this one because it's nice looking. And here we have what's a really modern and nice looking equalizer. But this does the same thing as the controls that say, low, mid, high in your car. Or it's the same as what's on your stereo or your mixing board, right? The frequency spectrum is the same, and we're just kind of manipulating it a little piece at a time. So let's play the loop back and see what the EQ does. Actually, let me turn this down a bit so it doesn't blast you. See if this works. And then I'm gonna sing another song for you, and we're gonna record the signal into the sound software. It's gonna be so cool. And then I'm gonna sing another song for you, and we're gonna record the signal into the sound software. It's gonna be so cool. So check out what's going on here. Let me just take a picture of it while it's moving, and then we can talk about what it is. Gonna record the signal into the sound. Okay. So this is showing us a pretty close to real-time representation of all the different frequencies that are in my voice when I recorded that. So it's across this whole spectrum, and this is the spectrum of human hearing. So we have basically between 20 hertz, which is really low end. You don't really hear 20 hertz. You can more feel that that's an earthquake or something. And then we have 20,000 hertz, which is really high, and I don't think anybody really hears that high either. But that's the maximum cutoff frequency for what we can hear. So what the phone companies and stuff were doing, we're saying, all right, well, the human voice, most of the information is in this range, right? This is kind of not relevant over here, and this is kind of just hissy sound. So what if we just cut all that off, and then they would cut it here, and we'll say, let's start like there. And then, well, what does it sound like if we cut off everything? Well, we know 3.5K is important, so let's just go up to 5K. And we'll just cut that off entirely, like that. Obviously, they didn't have a tool that was this advanced that could be this precise, but this is the thought, the process here. Ooh, I lost my curve, you bastard. 5K, here we come. All right, so let's hear what that sounds like now. And then I'm gonna sing another song for you, and we're gonna record the signal into the sound software. It's gonna be so cool. And then I'm gonna sing another song for you, and we're gonna... Right, so it sounds a lot like a telephone call, because this is what they did to make a telephone call happen. So here's all the frequencies we can hear, and we can have control over some of them. Now, the early compressors that we're talking about here didn't have this level of control. Let's get back to some of them. The first ones that were usable that we think about were called graphics equalizers, and they're still around. You see them all the time. This is one. I have this thing. It's a graphic equalizer for a guitar. So you plug your guitar into here, and then it's split into 7 sections, and these sections are called bands, EQ bands. So if we look at this EQ that we had over here, I can put points on here, and these would also be, each one of these is a band. I'm just making bands, right? Like so, but the graphic equalizers, they were fixed to different spots. So here we have 7 of them, right? That's why it's called the GE7. It's the graphic equalizer, and there's 7 bands. Now there's 1, 2, 3, 4, 5, 6, 7 across this way, and then there's one more on the right. And this was just a master volume fader, so that one doesn't count. That's just the overall volume. This was the first actual one that was a graphic equalizer the way that we know it. And it was designed by this guy, Art Davis of Cinema Engineering. It was for theater. So he was trying to take films and play them back, and what was happening is they're recording the film somewhere and then bringing it to another room, and the difference in the rooms was making the wrong things stand out. So what he wanted to do was equalize that so it all sounded correct and flat, and like the low end was the same volume as the high end. So he made this device. Now, the frequency bands were all controlled by these fixed sliders, and these are everywhere. So here's a digital emulation of one, and it's got a ton of bands, so you can have all these different bands and make fine curves, or you could kind of draw a curve in them like this. And they're all the same, whether there's 7 bands or 27 bands, right? They work the same way, and you'll find them all over the place. They do the same thing. They all do the same thing. All the EQs do the same thing. Parametric equalizers came around, and these are the ones that you see more frequently in like your DAWs and on mixers and stuff. But like I said, they do the same thing. They're just controlled differently. So we've got these points along the line, and we can move the points. That's an important distinction. Not always, but the first one of these was invented by this guy, Daniel Flickninger, in 1971. some of these, the early fixed ones, here's an example of an early EQ. This is a very, very famous equalizer. It's called the Pultec EQP1A and the MEQ5 because they couldn't get the whole frequency spectrum in one device, so they split it into two devices for just to fit all the electronics involved. So Pultec introduced this in 1951, and what's super interesting about it is that there's no amplification in it at all. There's no tubes in it. Right? It's just, it doesn't turn anything up, which is weird. How does that even work? It's crazy. So an interesting thing about this is when you boost one of the frequencies, it's turning down all the other frequencies. It doesn't actually turn up the frequency. So that's why you don't need an amplifier. It's not, it never turns anything up. It only turns things down. So by turning down everything else except the frequency that you want, it's essentially the same thing as turning up the frequency that you want. But you might get a slightly different effect. That's how this worked. And then at the end, you just turn the whole thing up and you get a more equal frequency spectrum at the end. So this was interesting because it allowed you to do like two separate cuts. It's weird. You could do, let me get a Photoshop or something. You can boost and cut the same frequency at the same time, which is kind of weird. So let's grab just a new document here. Let's make that a little bigger. Get my pen, make it white. Use a brush, make it small. Okay, so the Pultec, here's our frequency spectrum. And we set the Pultec and we say we want it to just kind of affect this area here, right? From here and below. So we send the signal through and we say we want to boost this area. So the Pultec would actually turn this down. So now what we have is kind of looks the same, but this is, it's the same curve. It's just not as loud, right? And here was the cutoff point. You can see that dip there. But when you turn this down, what also happens around the same area is it kind of pokes out a little bit like that. It makes a distinct little bump that sticks out in a way that we like. So this was super beloved for the way that it did that. So we were cutting this frequency here, but at the same time it's also boosting it a little bit right around there. So that's great for a kick drum because you want to cut out the thump, but you still want a little bit of boost so you feel the hit in your chest. So this was used a lot on kick drums and basses. It makes good sense. And they're still around today. There's a lot of emulations of them. So let's go back over to our thing here. So here's the real one. You can see it's split into two. One of them was to control the mid-range and one of them was to control the lower ends. And here's a representation of Waves modeled ones. So these are digital representations of this equipment. And Waves makes a bunch of them. This particular one here that Waves made was modeled after Jack Joseph Puig. Is that his name? JJP. Who is a famous mixer. And every one of these pieces of old analog gear is different. So if you had a Pultec and your buddy had a Pultec and you put the same source through them, they were going to sound a little bit different. Same thing with a compressor or any of these pieces of gear because they were a lot of times handmade. I think they were around this time all handmade, and there was variance in the stuff that they used to make them. So now in the modern age, when we model these things, companies will go in and use very specific microphones and tools and electromagnetic, roach clips, whatever it is they use to replicate the sound of this classic gear. They're also replicating those variances. So the point I'm trying to make is we could take a real hardware Pultec EQP1A, and then we could put it up against one of these software emulations, and they're not going to sound the same. And you could say, well, the emulation doesn't work, it doesn't sound the same. But that's not the whole story, because you could also take another Pultec and they wouldn't sound the same either, right? If it did sound the same, something would be wrong in the emulation, because they were never the same. So that's interesting. So this is the Pultec. Its good uses were guitars, snare drums, and vocals. And you can get these from a bunch of manufacturers now if you want them. They're very simple, right? There's not a lot of controls on them, especially the mid-range one, right? There's only 2 knobs on it. Let's move on a little bit. Now, in the 1960s, API made another equalizer, and this is simple too. So this is more like what you would see on one of today's mixers, where you have the 3 controls. Well, there's actually 6 controls. There's 2 different knobs on here, on each one of these. There's the blue one and the white one. This was designed by Saul Walker in the late 60s, and it was part of the large mixing consoles that they used in the recording studios. So you'd have a 20 of these, right, in a big console desk. It was made with this op amp. Op amp is a electrical circuitry I'm not going to get into right now, but this is a legendary op amp, the 2520. They used it going on in a lot of different things. They still sell it. They still make it. They still sell it, and it goes in the lunchbox. The lunchbox is that little device that we talked about during the I/O and routing workshop that I have here on my desk. You can take these audio things. They're like, there's a PCI card or an ISA card or something behind it, like a computer card, and you can just slide it into the slot and mix and match these things. So they make them in really small 500 form factor hot swappable modules. You've heard these on tons and tons of records. This is a very Jack Whitey aggressive kind of sound. He loves this kind of stuff. It's commonly used on guitars and vocals, and what this means, it says proportional Q narrows at Q extremes. So what the Q is, let's pop back over to Studio One and look at the other equalizer here. So if I put a node here, I'm just going to call this a node, and I get some controls. Now, one of these controls is the volume. This just pulls my node up or down, right? Imagine this was analogous to one of the dials on the API thing or the Pultec. And I have a control for what frequency it is, so that just moves this frequency. Now, not all the older gear had the ability to move the frequency like this. They were mostly fixed. And I have one other control here, and that's called Q. So let's go back to the middle-ish here and turn this up. And let's play with the Q a little bit. So right now it's 1. So this is saying, I believe that's 1 octave. And if I raise this Q, I guess it's not an octave. It gets more narrow, right? So if I make the Q here 40, this is a very, very narrow filter, and it's only going to affect a very small portion of the frequency spectrum as I mess with it. Now, this wasn't even possible with the circuitry they had back now. This is like a surgical new 20,000 year 2000 kind of evolution of the equalizer. But more commonly, they were like this, a bell. And what this is saying about the API is that as you moved across the 3 different controls, let's pretend this was broken into 3 bands, as you move across them, the Q changes, so they get progressively more narrow as you go up in the frequency range, which is just an interesting byproduct of the circuitry that was used when they made it. So that's how it works. There, the API. Let's pop back over to the slides here. Okay, so the proportional Q narrows at Q extremes. So you would take this, and you can see the bottom one is lower frequencies here. Ooh. Yeah, so we got 100, 200, 300, 400 hertz. Down over here, these are filters, so you don't get to raise or boost the lowest frequencies here, 50, 40, 30. These are actually controlled here with these filter buttons. You're either cutting off all the frequencies or you're not. That was kind of the thinking with this. So you can't control those frequencies. It's not until you get to 100 hertz where you can start boosting and cutting things with the API. And this was different from the Pultec in that if you make a boost here, there's an amplifier that's actually turning up that signal. Dun, 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 dun. So you would use the blue one here to pick 100, 200, 300, 400, and then you use the white one to control either up or down, right? There's a plus or minus on it, and you can turn the volume of 100 hertz up, or you could turn the volume of 300 hertz down with this control, but you couldn't do both at the same time. You'd need 2 units to do both. You could also, then it's broken into a mid-band here. So here we have 0.8, that's in K, so that would be 800 hertz, 1.5, 3, 5, and then we move up to the high frequencies here. Now, I would use something like this. It's really aggressive, and the high frequencies kind of shine on it. It has a glistening kind of, I want to say Dave Grohl kind of feel, but I know this isn't what he used. But it has that kind of aggression to it. So I would use this on male vocals, or I probably wouldn't use it on female vocals because that's probably too much glisten. But male vocals that need to cut through a mix, or guitars that need to cut through a mix, or anything that you want to kind of stand out a little bit, but you don't necessarily need it to be the loudest thing in the mix. Boosting the high end with a machine like this would do that. And this is the real one, the 550A that you can still buy today, and this is an emulation of that Waves makes. So let me just make this bigger. So here's the software representation of that device. It looks almost exactly the same. It's a little bit cleaner, and they give you a couple more controls. One of the cool things about these Waves and emulations is you can turn the modeling bit on and off, which is weird. So when it says analog on or off, that's should we use all the noise and analog circuitry, or should we just turn all that off? Personally, I don't know why you would use an EQ like this, why you would even buy it if you were going to turn that analog button off, because the whole point of using one of these is to get the analog character of the circuitry. So I leave that on. This is the API 550 in the 1960s. And I want to talk a little bit about dynamic range. It's kind of jumping away from EQs to compressors for a second, but let's talk about dynamic range because this is where I put the slide. So the dynamic range is the difference between the quietest parts of the audio, like in here, where there's not much sound, and the loudest parts of the audio. So just like in photography, you have a dynamic range of an image where the darkest bits of the image and the lightest bits of the image make up your dynamic range. So a lot of times maximizing the dynamic range of something is very good, not always though. So in this example, you can kind of see steps, and this is the same with amplitude of sound, right? So the dynamic range is the difference between the loud parts and the quiet parts. That's all it is. And compressors are made to control that dynamic range. I'm going to show you a more advanced example of using a compressor to do what's called audio ducking now, because I want to show you how the compressor itself works, and that's going to be a good example. Thank you. All right. So now we're back in action. All right, and here we go. So what we have here is 2 tracks. I've recorded me speaking here, and then this is the music that we pulled in to listen to, the circus music. So what happens when I play the music alone without the speaking, as you can hear, you can see the frequency representation here at the top part of the console. What I'm doing over here, when I play both of them at the same time, you can see another signal that comes into the bottom of this compressor. Thanks, Lisa. But if you're interested in learning more about microphones, then now you can see when there's a signal here when I speak, it tells the compressor to turn it down by whatever I set these controls to. So I'm just kind of cranking it down so it turns it down a real lot. Listen. So it just recorded a loop of the same thing. Ba 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 ba. But if you're interested in learning more about microphones, then I recommend you check out our previous workshop on microphones, which happened last week. It's on my YouTube channel. You can find that at www.youtube.com/Luke McNeil. So you can hear it turns and see that it turns the volume of the music back up when I'm not speaking. What I'm trying to show you here, though, is how this is split into 2 sections. There's the part that's feeding, or there's the part you're listening to, and the part that the compressor is working on, and then there's this side chain thing. And the side chain is the signal that the compressor is looking at. So I just want you to understand that there's the two different signals, and that's important when we get into the electronics of this. So let's pop back over to the slides and move on. I'm glad somebody's watching and telling me when something like that happens, because I'd just keep going forever. Let's talk about magnetic tape for a second. It was important. It was created around 1928, and magnetic tape worked. Actually, there was something before it that was similar to magnetic tape. It was actually wire. So it worked the same way as a tape machine, and you had a spool of wire. It looked like solder, but it was way thinner, and it would one side would spin, and there would be a little magnet on one side that magnetized it as the wire moved, just like tape. But we found out just tape was better. Tape was just better and cheaper to make. So when we found out tape in 1928, Fritz Flumer figured it out in Germany. He had built it off the designs of that earlier wire recorder, and he used paper initially for the tape and sprinkled an iron powder. It's actually, today, in the tape that we all know and love, it's actually rust. It's just plain old rust. Now, the paper got pulled through a thing, so they had, well, like a printer would pull paper through, kind of, but more primitive. At a steady rate, the powder got magnetized, kind of like if you think of those faces with the magnet dust that you could draw the face on the dude. It was kind of like that, but it was all on this paper. And he found out that as we magnetized that, it would save basically this. If we look at the audio again, it would do basically this with the particles and make a waveform and save it along the tape as the tape moved. So instead of this just being bits on my hard drive, it was bits on the tape. Same thing, though. Same basic concept, which is crazy. Thing about tapes, well, let's finish the slide. So the magnetophone was the first practical tape recorder. It was made in Germany in 1935, and it was like a dictation machine kind of situation. So they were still thinking along lines of phones and voicemail and short audio messages. It wasn't. Nobody was even considering music as part of this right now. This guy, after the war, John T. Mullen, figured it out with backing from Bing Crosby. So Bing Crosby was a big deal during the war. He was like, somebody said, I think he was the most important thing America had during the war effort because he went over, he made the troops happy or whatever. We have a podcast on Bing Crosby if you're interested. It's called Know Your Celebrities of Yesteryear. Bing Crosby and Bill Cosby. That's also on the uncannyvalley.net. I recommend that you check it out. But yeah, Bing Crosby put a lot of money and effort into this development because he was a nerd. He was into it, right? It was his Guitar Center. They didn't have Guitar Center to go to. They had to like hire people to invent stuff for them. Ampex took this and created the first commercial like tape recorders in the late 40s. So tape's been around quite a while. And it was the fuel, I guess, for a lot of these recording studios. One of the characteristics of tape, though, is compression itself. So we are using machines to control this compression, but actually the tape itself does this. So and we like the sound of it. So you can hit a tape with a signal that's louder than the tape can represent. So if we look at this, like what happens if we slammed the tape with this? What would it do? There's nowhere for the additional volume to go like there is in the computer now. I could do that all day on the computer and it's not going to matter. But if this was a tape, I mean, you've only got an inch or whatever of physical space to represent your sound on. So what happened when we maxed that, and people did it on purpose, is it would get a form of compression. It would actually turn these bits down, the top bits, in a way that we really, really like. And we know because we listened to cassettes, or at least my generation did. So we're familiar with the sound of that tape compression, and we go through an awful lot of work now to try and emulate it. So, yep, here we go. Audio was recorded using magnetic tape with large tape machines. A byproduct of that was dynamic range compression. That's me showing. I showed you how the amplitude works. Another byproduct of using the tape is obviously noise. There's a lot of noise with tape. It's a magnetic thing. There's interference from other things going on. There's speakers everywhere, which are themselves magnets, so those are causing interference. So there was a lot of noise with tape, and that was a problem. And it kind of it informed the decisions of the recording engineers at the time as to how loud they were going to record their signals, because they had to record a signal that was loud enough to be heard over all that noise, and that was important to them. We don't have to worry about it too much now. Now we're getting into some basic compressor controls. So you see these, depending on what you're working with, what your audio software is, you're probably not going to see a compressor on a home stereo. You might, but if you're a musician, you're going to see these in guitar pedals and guitar amps and DAWs and anywhere that you're working on an audio signal. There's really only 4 main components to a compressor. You have the threshold. The threshold is the point on the compressor at which the compressor is going to engage and do something. So you're saying when the audio gets above this level, I want you to do something. That's the threshold. Then there's a ratio. The ratio, if you think about a compressor as a machine that's turning a signal down when it gets loud, the ratio is how much the signal gets turned down relative to how loud the thing is. Should it be 2 to 1? Should it be 4 to 1? Should it be 100 to 1? Do we want to just limit it off entirely? How much do we want to turn down the signal? That's the ratio. Then we have an attack. The attack control on a compressor sets how fast it should start turning down the signal. And there's a lot of different reasons you would want to control how fast that happens. I'll show you some. And the release is the opposite of that. It controls how long it should take the volume to come back to its normal state after it's been engaged. And these are sometimes, depending on what hardware or software you're using on a compressor, you may have all or more of these buttons or not all of them. They might be called different things, but every single compressor works in this way. Sometimes the attack and release controls are built into the physical circuitry of the machine. Sometimes they call it whatever proprietary thing they call it. Okay, so we're going to start looking at some compressors and how they worked. This is the Big Daddy compressor of all Big Daddy compressors. This is the Fairchild 670. This thing was massive. It was very expensive. It's what was called a Vari-MU compressor, and all that means is that this was based on tubes. Now, a lot of the other circuitry that we've talked about, all the preamps and stuff that we talked about, that stuff, it used tubes to turn up a signal. This thing was actually using tubes to turn down the signal in an interesting way. So it was created by Sherman Fairchild. He was the son of one of the founders of IBM, so he had a lot of money. His dad was a genius. His name was Vari-MU, and no, this is wrong. I'm saying it wrong. So Fairchild's dad was one of the founders of IBM, and that guy hired an Estonian genius and licensed his compressor design to make this. That's what happened. So Sherman Fairchild broke off with Dad's money and was like, I want to build the coolest compressor anybody's ever seen. And he had heard about this other guy, Vari-MU, and he hired him to come make Fairchilds. The 670 is a stereo compressor, so it had 2 channels. It included 20 tubes, which is insane. There's 20 tubes in it, 11 transformers, and 2 inductors. That's a lot of circuitry. It was very heavy. There's a lot of parts in it. There's a lot of maintenance involved with it. I mean, finding a tube is difficult. Finding 20 tubes is going to be difficult today. There was also another one that was only a mono one, and that was primarily intended. The purpose of it was to protect radio broadcast transmissions. Because there's a thing that would happen where, if we play a sound that's too loud through something, we get distortion and it sounds bad. But if that signal gets too loud when it's radiating off an antenna, like a radio wave, it results in a thing called overmodulation. And the overmodulation, when the amplitude or the volume of the sound gets too loud, it messes up the whole transmission on the radio waves, and the stuff on the other end can't read it anymore. It's like syntactically incorrect now because it's been ruined. It's been overmodulated, right? So this was intended to protect radio broadcasts from overmodulation. It would cost a radio company a lot of money if they were selling advertising space to somebody and then the ads didn't run because of whatever. So they made sure that anything that they could protect and ensure that the broadcast was going to be safe, they would do. And they were designing these insane machines to do that. So aside of that, another purpose for this device, and you can kind of tell from the way that it's labeled, it's easier to read on the emulation one than on the real one. Let's look at this. They have these controls here like lat and vert. These were controls that were relating to the cutting lathe. So this was also protecting the vinyl cutting lathes from getting too loud. So this was used in a process that was then called mastering, where an engineer would take account of all of the technical specifications and limitations of working with vinyl, and they would make sure that the recording made it to the vinyl without messing anything up. Because if there was a mistake in that, if there was a mistake in the press, and then you made 100,000 records that people couldn't listen to, it would be very, very expensive and tarnishing. So this is an example of the Fairchild that's been modeled after one that's owned by Jack Joseph Puig. Same as what was the other Puig thing we looked at earlier? Was it the Pultec? So he's got a Pultec and he's got a Fairchild, and Waves worked with him to model his gear, and that's what this is. So this is his. And this was one of the earlier ones, and it was, like I said, primarily intended for broadcast and the cutting lathe. Now, recording engineers or people that were making music were they were paying attention to what was going on in broadcast, because this was exciting stuff. Think about, especially back then, how many musicians were super sciencey. Like Joe Walsh is a really well-known ham radio operator. Those guys are really into electronics. Brian May, astrophysicist, builds his own gear. A lot of musicians are also electrical kind of tinkerers and even beyond that. So these guys were legitimately interested in not just what it could do for them, but they were interested in the circuitry too, which is cool. So tons and tons and tons of hit records have run through the Fairchild. You've heard it from U2, Stone Temple Pilots, No Doubt, Counting Crows, Green Day, John Mayer. Tons of people have used the Fairchild. It was on pretty much every Beatles vocal from Revolver all the way on. They loved it. And they didn't make a ton of them because obviously there's a lot going on here. And they were very expensive. Now, after that, we get a new compressor, the new kid on the block. This works in a completely different way as the Fairchild did. The Fairchild used tubes to do its compression. This uses light in an interesting way. So this is called an optical compressor, and it's a super famous one for a couple of reasons. One, there's two controls on it, so there's nothing to learn, right? You could put this in a radio station and give it to an intern, and they would have to work really hard to make it sound bad. So this is beloved for that reason alone. It's just super easy to use. Now, you'll see when we talked about the controls of a compressor, we had the four controls here: threshold, ratio, attack, and release. But if we look at the LA2A here, there's really only two. There's one that says gain, and there's one that says peak reduction. And the thing about this compressor is that the other factors are built into the circuitry. The attack and the release are built into the circuitry. And they're dependent, like heavily dependent, on the signal that goes through them. It would react differently to different types of music, different speeds of music. It would actually take into account the beats per minute of the music and all that stuff, just inherently by the way that it worked. Now, this used an optical sensor and a voltage-controlled light source to apply resistance to the source signal. So let's talk about this for a second. Let's pop over to our compressor. This is why I showed you the compressor in the beginning. So what's happening is there's two signals here. When we hit the compressor, the signal gets split into two separate signals. They're copies of the same signal. In this case, we fed a different signal. But let's kill this sidechain. So doing apples to apples here. Let's get rid of this. So by default, let's just work on the music. Let me turn it down a good bit. All right. So by default, you can see here, I'm only playing the bit where the music is playing, so my voice isn't part of this equation anymore. Right now, what's happening is the signal here, when it enters the compressor, is just being copied. And there's one half of it going to the side chain here. That's what all these controls are looking at and controlling. And when we adjust the threshold here and this line moves, this is what it's moving along, right? So it's looking at this signal. It's saying, all right, when this signal passes this threshold, I want you to turn down this other signal. That's how it's working. So it splits them in two. And that's how the LA2A worked too, except it used some crazy optical sensors. So let's pop back over to the slides. So imagine this has a side chain, and we send it our bass guitar signal. And the bass guitar gets to the machine, it gets split into two, and then one of those is looked at by this peak reduction thing. And we say, all right, how much do we want to turn the peak down? And then the peak reduction sets how much the volume comes down. So the side chain is coming through here. It's coming through here. It looks at what you want this set to and how much of the signal is going to have to be altered, and it sends a voltage to a light bulb, basically a little LED type light, and that glows physically. It really does. It glows, and it glows at a certain brightness relative to how loud the thing is. And then across from it, like a little bit, there's a photo sensor that reads how much that light is. And however much of the light the photo sensor picks up, that's how much it clamps down on the signal. And the attack and the release, the other characteristics of the tape machine, are built into how long it takes those lights to just cool down and warm up and cool down and warm up. So we don't have a control to change that. It's a characteristic of the photo sensor in the machine that is setting that. And it's different because it sends a hotter signal. On louder things, it's going to be different on faster things because it takes a little bit longer to recover. So it has a characteristic sound that is, it's kind of smooth and slow. It's not aggressive. It gets out of the way easily. Like it doesn't stomp on sounds. So actually, what I'm talking to you now through is modeled after this very compressor. I have a hardware LA2A modeled compressor in a 500 series unit, and my mic right now is going through it. And when I speak, it's turning down the louder words that I say by about 3 decibels. And now that I've turned down the louder words by 3 decibels, if I turn the whole thing up, if I use this other control here, the gain, and turn it back up by those 3 decibels, now the sound overall is more even, and it gives me the ability to move back a little bit from the microphone, and it's kind of evening that out, so it's not as in and out, in and out. It should be more clear and more coming from the center, and my words should be around the same volume, even though when I speak them, they might not be. This is helping to do that. So this is tube driven. It was really intended for broadcast for the same reason they were trying to not overmodulate signals, and also it was for the reasons that I said. It's making my voice more clear. It's making me cut through other things like noise easily because the density of my now compressed signal is more solid. This particular emulation, Waves also makes an LA2A. This was modeled after Chris Lord-Alge's LA2A, and he's another famous mix engineer that is known for his use of compressors, very heavy compression. People don't like him because he uses so much compression. It made things loud, and then we had the loudness wars, and it was a whole thing. But this actual model came after the LA2A, the Teletronics LA2A that Chris Lord-Alge owns in his studio. You heard this. Prince used it It's Born in the USA went through this. Green Day's American Idiot, the Rocky V soundtrack. This is a big deal. A lot of people have it, and you've heard it a lot. It's easy to use, so this is a good option for a lot of things. It's great for bass. It's great for vocals. In 1955, I alluded to this in one of the Facebook posts earlier. In 1955, we get this crazy thing, which was developed by a guy named Ross Snyder of Ampex at the time. Multi-track recording. So they had, they were recording to tape and stuff, but this is the first time we could record multiple tracks at the same time to a tape. The invention of tape enabled sound engineers to record their own parts to different parts of the tape. The tape was wide enough to support more than one sound source, more than one of these waves. Like if we look at our digital representation, the physical tape itself was wide enough to do something like this. And then let me just duplicate this a few more times. Whoop. Duplicate complete. Doop. So all of this information could be stored in discrete, its own little lane of the tape, which is very, very cool and new at the time and fancy. And everybody was like, "Ooh, I want that!" But it was expensive, really expensive. So Les Paul bought this. The Les Paul that invented the electric guitar and a bunch of other stuff. He was a real genius, American legend, Les Paul. He paid $10,000 for this thing. There was only one of them. They called it the Octopus. Les Paul and Mary Ford used this to record their tracks, which were, I think there were hits at the time. I don't know, sure, but some famous recordings have been recorded through this particular machine. And you can see there's not much to it. There's volume controls. There's, I assume these are little EQs, little parametric EQs. High and mids, I'd guess. Building off of that thing, we start to get Abbey Road Studios. They got the Beatles and a lot of momentum for them going around this time, right? So they're investing in making music and new technology. So they have their own in-house guys building stuff for Abbey Road Studios. And this is EMI Red. This was one of the first, a mixing desk as we know it. Now, this was entirely vacuum tube based. There's a lot of tubes in this. It ate a ton of power, obviously. It had 8 channels like the Octopus, and it had bass and treble controls. So super simple EQ. You can turn up the high end or you can turn up the low end. So this is the classic sound of the 60s. You definitely have heard this on many, many records. Its precursor was the Red 1.7. Red was a line of machines. They kept kind of iterating over them as different technology became available. But the Red series all share that British characteristic sound of the Beatles. It was used to record nearly all the Beatles records and the first couple Pink Floyd records. So that sound, that 60s sound. This desk was designed to feed a 4-track tape machine. So the output of the desk itself was designed not to go necessarily to, it just went to a tape machine. Whole output went to a tape machine. We get the invention of the audio cassette. Remember those things? Philips Norelco invented the audio cassette in 1962. It's pretty much the same thing as the tape machine. It's just smaller. The tape in the cassette tape was able to be smaller because it didn't have to have any margins around it for people's fingers. You had to handle real tape, or not real tape, but the old school, 1-inch tape. You had to handle that. This was it was encased in the plastic, and nobody ever had to touch it, so it could be thinner. So this works kind of like you see here. The tape is driven by a guide, and there's a few different heads that lay along the tape. There's an erase head, and what the erase head did was it magnetized the tape right here with a really, really high frequency, really, really loudly, a frequency that we can't hear. So it was not really erasing, it was just kind of scattering all the rust and the particles that were living in between the plastic on the tape. So erase it first. Then there's a record head that would magnetize as it went along. So you got erase and magnetize right there in a line. And then there's also a playhead, and the playhead was what would read it. So this is record. You use these for record, and you use this for play. Then they had what was called the capstan, and I'm pretty sure the capstan is the part that turned to pull this tape. But somebody like Mick Lawless could probably correct me there. I don't really know the anatomy of the tape too well, but this is, in essence, how it worked. Even the reel-to-reel tape machines, that's how they worked too. Now, the cassette was designed and marketed to like business people because this was supposed to be for dictation. Men didn't type back then; they weren't expected to type back then, and they would say their thing and have a secretary write it. But this would allow that to happen kind of outside the boardroom, and that was really its primary purpose. But noise was a big issue with tape because all of this is loud, and there's a lot going on in the world just physically that interferes with this and adds noise to the signal. So it was a big, big issue until this guy came along, Ray Dolby. And you know Ray Dolby, the Dolby Digital, the double Ds. He saved the day. He figured out how to get rid of a lot of that tape noise, and he did it kind of with EQ, with an equalizer. And I'll explain that to you. So, actually, this is just a fun fact. The Ds in the Dolby Digital symbol are designed to look like tape heads. They're supposed to be these. Because they started as a tape noise removal company before they were the stereo, surround sound, Dolby Atmos, all that stuff. They were getting rid of the noise on the tape for us. So Dolby just kind of found where the noise was on the tape in the high frequency areas, and he would use an EQ to cut that down. So you cut down the EQs in the high area, but the problem with that is then all the parts that make the speech clear kind of get altered too, and things start getting a little more muffled, more muddy. It's harder to discern words between other words. So that was a problem. But Dolby figured out if he boosted the EQ first, right? Let's make the noise louder first. So this happened in the record process. When he was recording, he applied EQ to the noise on the tape. Now he records, and there's an artificial boost in the EQ around the area where the noise is. And you record to it, and if you were to listen back, it would sound like there was too much high end. But then Dolby, on the other side of the record process, applied EQ to remove his same boost. And with that, he removed the noise. And the original signal just came back to where it should have been in the first place. And that's how Dolby noise reduction worked. It's kind of simplistic if you think about it, but at the time that was super revolutionary, and it solved a really big problem for a really lot of people. Okay, moving on. Here we go. Universal Audio in 1968 comes out with a new type of compressor, because if you remember from our previous discussions before this time, this is when the transistor is getting very, very popular. It's invented, it's cheap, people are using it, studio gear is suddenly becoming affordable so that you don't have to go to Abbey Road Studios anymore. There's more studios popping up because they can buy the stuff, because there's not a million tubes in it. So this was designed by Bill Putnam. He's the guy that founded Universal Audio. That company is still around today. It used solid-state FET circuitry to do basically the same thing that the other compressors were doing with tubes. It has some characteristics that are interesting. And this is also emulated in a lot of other like DAW software. So if you just pull up the compressor in your DAW, it might be this. I know that Pro Tools has one like this built in. And look at the controls on it. It has an input, an output, attack, release, and ratio. So it's got almost all the standard controls that you would expect, but it works a little bit differently. You don't set the threshold. The threshold actually gets set by mixing these two together. So how much you drive the signal into it sets the threshold. And it's not linear. It's a scale. It reacts differently based on the source material that you feed into it. So you play with the input and you drive the signal into this compressor, and it compresses. And you can set how much it compresses here by setting these buttons. So it could be 4 to 1, it could be 8 to 1, 12 to 1, and Now, on the emulations, you have another button here that says all, but this didn't exist on the real ones. On the real ones, you had 4, 8, 12, 20. And engineers that were using it learned a trick where if you pressed all the buttons in at the same time, it had a completely different effect. So emulations love that, and they added the little all button to simulate pressing all the buttons at the same time. And it had attack and release controls on it, which kind of work backwards from regular attack and release. I think this over here, the lower numbers are slower, and the right number, 7, is faster, I think. I always get confused which way that goes, but yeah, I think that's correct. And same with the release. So you can set those. And this is very fast. It got the transients of things that were too fast for the tubes to react to, or for the light diodes to whatever you call the light sensors to react to. This was way faster because it was all solid state circuitry. There was no tube to wait for. There was no light sensor to wait for. It was just instant, which is different from anything else that had been on the market and had a crazy sound. This was also modeled after, the Waves emulation anyway, is modeled after crystal orologies. And there were more than one revision of these things. This thing had a few different faces to it. It had a black-faced one that they call Blackie, and it had a blue-faced one that they call Bluey. It was really silver-faced, and there was one more of them. So if you buy like an emulation package, you might get 3 of these, and they all kind of work the same way, but with a little bit different characteristics is all. The 1176 is another super famous compressor. I have one here in my rack. I'm not speaking through it right now, but it's not this exact 1176, but it's been modeled in the same way. So most of the compressors that we get today are modeled after one of these other compressors that kind of set the standard, at least in the way that they work. I mean, I'm not saying there's not innovation, but there's also a consistency. So here we go. In 1970, we get the Helios console, and this was a big one. This is the Jimi Hendrix console. Eddie Kramer used this console. He's a famous recording engineer that recorded like Led Zeppelin, Jimi Hendrix, and Kiss, people you might have heard of, the Eagles, Bowie, Zappa, Clapton, Frampton, Queen. That sounds like a band. That should have been a super... Clapton, Frampton, Queen. Could you imagine that? Could you imagine... Ooh. Imagine like Peter Frampton / Freddie Mercury. Like Freddie Mercury through the Peter Frampton box. That'd be madness. Whatever. The Who recorded through the Helios. This is the sound of classic rock as we know it. This was designed by Dick Swettenham of Abbey Road Studios. He designed it for Olympic Studios in the early 70s. Eddie Kramer had this for a long time. It had 38 channels of Helios type 69 EQs. So this is what each of the channels looks like. Here's an emulation of just one of those 38 channels on this board. So this is kind of what they were like. So built into this thing, you have the preamp, so that's just volume, and then you got your highs here, 10K, and then you have the mids, which were somewhat adjustable, so you could pick where the midpoint was, where the node would be on the line, and then the bass boost, and yeah, so basic stuff here, and then your input and output levels. So I don't think the original console had input and output levels. There's probably one output, like a master output, and then each of the channels had its own fader. And then this is interesting. Here we have some buttons. We can turn the noise to original, like the original noise of this console, which was noisy. If you think to those recordings, they're really noisy, Jimi Hendrix especially. Or you could muffle that, baffle it a little bit, and turn that to low. And then over here we have analog 50 hertz or 60 hertz or off. This is actually made to model the sound of the electricity. If you wanted it to sound like it was British, European, then it would be 50 hertz. And here in America we use 60 hertz. So that has a different sound to the noisy hum, which we can model here. I keep that off myself, but we could. So this is the Helios console, and it was a big deal, and a lot of people used it. Now, in 1973, we get the Neve 8020. This You might have heard of the Neve name. I'm sure you have. Neve's been around a long time, and he's beloved in the industry. This was a big deal. This design was by Rupert Neve. It was transistor designed, right? So there's no tubes in it. This is the sound of 70s rock. This is the aggressive, rocky, like angry sound. Dave Grohl bought this, the mixing board, the 8028 mixing board from Sound City for his personal studio because Sound City hasn't been doing well. This is what they recorded Nevermind through, and also so many other classic records: Tom Petty, Metallica, Fleetwood Mac, Johnny Cash. There's a documentary on Netflix that's called Sound City, about Sound City and a lot of the bands that recorded through this particular console, and why Dave Grohl in particular loved it so much. And it's really cool that he bought this, and now he says he brings new bands into his studio, and they just come in just to be in the same room with a thing that's the thing that recorded Nevermind. Can you imagine that? He said that they come just to smell it because it smells like burning wires. It smells like it smells like rock and roll. So this thing is awesome, and it went into this tape machine. It was a very famous pairing at the time. This is called a Studer tape machine, and it had its own sound too. And these were paired, and now this is how Dave Grohl has his studio set up with this gear. It's kind of cool. In 1976, we get the DBX160A VCA compressor. VCA stands for Voltage Controlled Amplifier, but it really is turning the signal down. It should be Voltage Controlled Attenuator. This was invented by Mr. David Blackmere in Waltham, Massachusetts, 1976. We actually, some of us that go to the Rose Garden open mic there, we had the pleasure of spending some time with his son, who's still around here. He plays the bass, which is interesting. So the DBX company is from around Massachusetts, and they're still active. I think Harman owns them now. They were bought out, but they're still innovating. They're still making stuff. Anyway, this compressor particularly was a solid-state compressor. It was very, very fast because it was a solid state, so it didn't have any tubes or anything to wait for. And this one in particular produced way less distortion when you hit it hard, like really hard. Other compressors, like the 1176, you could hit hard and they would make a sound. Like there's a distortion introduced. It's in many ways favorable distortion. Like we like the distortion it makes, but it's not always what we want. So this particular compressor came out and kind of solved that problem. So a lot of people use this on drums and on the whole overall, like the whole mix at the end of recording everything. You might put something like this over the whole mix. I wouldn't use this on the mix, but some people do. It adds a punch. It's great for drums and bass. The DBX 160A. Not much going on here. You got a threshold compression. This is kind of like a ratio. And you don't get to set here the attack and release times. It's just fast. And then now we get, this is kind of, I don't want to say modern times, but this is probably this kind of changed the mold for a lot of people. So the SSL 4000 series console was created by Colin Sanders. He originally worked to make pipe organs. And this guy was into recording. He was an enthusiast about recording, and he wanted to make a console. So he recorded music himself, and he was like, recording's kind of a pain in the ass. At the time, up until 1977, all they had on these mixing boards was just the basic EQ. And if you were going to use a compressor or anything like that, there was a patch bay involved, and you had to get the patch bay, and then you had to patch it in, and you could only use it on one channel at a time, and then it was finicky, and then you had to have cables everywhere, and it was a pain in the ass. And it was touchy, right? So this guy Colin comes around, and he's like, well, why don't I make a console that has the compressor built in? And then everybody was like, whoa. That changed mixing forever. So he has here an EQ and a compressor and also some other dynamics tools like a noise gate. He put them all on every channel. So there's no need to patch in a compressor for any channel. You could put them on everything if you wanted to, and a lot of people did, and they sounded great. So this was able to solve a creative block. It takes time. It takes you out of the zone when you have to grab a patch cable and be like, all right, the input of this one goes into the output of that one, and something's not plugged in right in the back. So it got rid of all that, like that time sink, and allowed people to just make music and be in that space, which is a big deal. So that was huge. Later versions of this console also innovated further in that up until now, on all the mixing desks, if you were working on a song and you had to step away for a minute, somebody had to come in, like an intern or something, and write down every pot and every fader level on a piece of paper. And that's how they would save their presets. That was their settings. Or they would have like a wax pencil or something and mark where everything was. But obviously that sucks. The SSL series changed that in that you could save the settings of everything on this thing onto a 5 1/4 floppy disk. And that was huge because those things were transferable. So you could grab one of those big floppy 5 1/4 disks and save your song preset to it. I think every song was probably its own disk. And then you could bounce between studios. So up until that point, if you wanted a piece of gear that was at a studio, you had to go to that studio. It was hard to get anything like this. You couldn't move one of these consoles around. So producers would pick the studio that they made the record in based on the kind of characteristics, the sounds they wanted. This allowed the engineers to be like, all right, I worked on this over at that studio. I got the vocal tracks. We had the Pultec over there, and we had the Fairchild, but now we're over at this studio now. We're going to use the 1176 because it had a particularly good sound in one there for whatever reason. It enabled the engineers to do that, and that was huge. So that they called it total recall. It was the ability to save the location of every pot and fader on the entire console to a floppy disk. You heard this console on Tupac, Bon Jovi, Breaking Benjamin, Britney Spears, Candiria. This is more than any of the other ones, right? This is just alphabetical order, and I was kind of scrolling trying to get down, find good samples, but I could just read it in alphabetical order, and it's a list of who's who. Interestingly, though, on this list we found this band Candiria. That I did not expect. The Candiria is a band that my brother Eric and I used to love when we were teenagers. They are like a metal band from New York, like a death metal band, not death metal, but kind of like screamy metal band. And but they would stop in the middle of their metal and just break out into crazy jazz bits. And they had horns, and then one of the dudes was a rapper. They're just a very interesting band. And I didn't know that they had that kind of clout, that they would be on a list of notable users of the SSL 4000 series console. Anyway, this is a quick walkthrough of some famous pieces of gear here and how they work and why you might use them. Now we're going to take a break and come back, and I'm going to start doing some examples of using EQ and compression and seeing like exactly how they would work for practical purposes for you. Cool. All right. And we're back. Welcome back. So we just took a look at some of the compressors and equalizers throughout history. Now, what I really want you to take away from that whole bit is that these things started primarily to control just a speaker's voice over the radio, right? We were just trying to make sure that the signal didn't get too loud so that the radio transmission didn't get messed up. Then we started messing with equalizers because the film industry was making some films, and then they were taking the films and playing them back elsewhere, and it didn't sound very good. So they came up with a tool to equalize the sound afterwards. And everything after that, and all those primitive controls, is just a little revision, a little tweak in the way things are done, until about the 60s and 70s when sound engineers started figuring it all out, and we started getting real enthusiasts like the Les Pauls and the Beatles and people like that. And they took these tools and started applying them musically to the art that they were creating. Now, all the tools that we talked about earlier are old analog tools, and they had a lot of limitations that we don't have today. Today, things are different with the computers, and that noise, if we don't want noise to exist, we don't have to have noise exist at all, right? We don't have to worry about a noisy tape machine. We don't have to worry about electromagnetic interference in the tape. We don't have to worry about bad cables, like the whole bad solder. Our manufacturing process is way better now. Everything about our gear now solved the problems of before. The thing is that it introduced a new problem in that when computers started coming around and people are using Pro Tools now in the studio and transistor electronics are super cheap, the problem became when people were producing records now, they had a different kind of sterile property to them. They were very clean. They didn't have that kind of grunge, that gritty fullness that we're all used to from listening to all that distortion and noise. And another important thing to consider is that old analog gear, when you pushed that stuff too hard, when it distorted, it always distorted in the key of the song. It distorted in a musical way relative to what you were putting through it. But when we found out when we distort the digital converters and stuff, that's not the case. You just get random, unpleasant, awful noise that is not. It's not the same thing. So we don't play with the level the same way through the digital gear that we did with the analog gear. What we have done though is emulated all that analog gear and put it into the digital realm to solve this problem. Because now we can selectively put the distorty parts that we liked, the characteristics of the old British consoles. We can put those on just one track. We can put them across all our tracks, and we don't have to have a team on site to change tubes and crawl behind the machine when it breaks. It's just we slide it onto the track, and that's it. So cool. Let's take a look at EQ. We're just going to bust into using an EQ. Now, I'm going to switch over to my desktop before Lisa yells at me for not showing my desktop. Here we go to the desktop. Yeah. All right. So here we have our circus music, which I love. And I'm going to grab, well, it looks like I've already got some stuff on here. Let's get rid of whatever's on here. Let's get rid of the send to. Go away. It won't. All right. Cool. I'm going to grab this EQ here. Let's pull it over on that. And this particular EQ that I'm using right now it's by a company called FabFilter. It's the most amazing EQ on the planet. It's kind of expensive. It's about $200 if you have to buy it, but it is amazing. Now, this particular EQ is not made to impart a character like the EQs that came before it in the API and stuff. Those were intended to sound a certain way. This is supposed to be clean and transparent, and it's a tool for it can be surgical, when those other tools just couldn't. So I'm using this as an example because it's really well laid out, and I can show you a lot of stuff with it. Now, one other tip I want to give you before we get into the nitty-gritty here is if you're going to buy anything that's audio related, any of these plugins that you see me use or that you read about or whatever, never, ever, ever pay the full price for a plugin. Just don't. You could get sucked into paying a lot more money than you have to pay for a lot of this stuff. So pretty much any bank holiday, all these audio companies will put their stuff up to 50, 75% off. On Black Friday, it gets even crazier. So if you're on the market for this type of tool, I'm not suggesting that you buy anything. You don't need to. Just if you're going to buy stuff, don't just buy it from the manufacturer for the list price. You don't have to. All right. So let's play our circus music and see what the EQ does here. Let's see. I don't hear the circus music. There we go. Let me turn it up. And let's turn off that freeze I put on here. Music's perfect. Okay, so what we see here is a representation of all the different frequencies that are playing along with the sound, and as close to real time as we can, proximate, whatever. So this particular EQ gives us the availability to add a little point anywhere we want to control frequency. So let's just add a point here and sweep it across the frequency band so that you can hear what each part of the frequency spectrum sounds like. So I'm going to turn up the music, and I'm going to shut up, and I'm just going to sweep along the frequency curve here. Turn it down a bit more. So here we go. I'm starting at 20 hertz here, which you shouldn't hear unless you're in a club. Now we're around 1680. Now we're at about a 250. Here's 500. Now we're around 1,000. And now listen. We're at about 1,000 hertz now. So listen as I move up towards that area where we looked at the ear, about 3.5K. That area, it's probably going to sound pretty annoying. So just pay attention to that particular area because it's super important. Because one, our brains interpret it louder than other things because of that canal. Because the canal in our ear, it resonates when sound goes through it, and it turns up the frequency around the area we're about to get to. Also, it's become evolutionarily important to us because that's the same area where all our speech happens, and also that's like where a baby cries. So that sound we can hear louder from farther away than other sounds. So just listen to what happens when we move this up to like 3,000, 3.5K-ish. Okay, so it's kind of hurts a little bit, and then let's keep moving up, and it'll get higher and higher in the frequency spectrum as we move along until we get up to about like 17 or 18, where we stop hearing. So let's go through this kind of exercise one more time. I'm going to set that loop to so it's a little bit smoother, so the sound doesn't stop anywhere within it. Let's grab this louder. Let's loop it here. See what that sounds like. Ooh. Start there. Okay, cool. So now we're going to do the same exercise, but I'm only going to I'm going to allow the sound in the frequency range we're boosting. That's the only thing we're going to hear. So let me make this a little bit more dramatic. We'll start back down here, and then I'm going to start sweeping, but I'm only going to sweep this particular frequency, so that's all you hear. Ready? Let's go. So down 15, you're probably not hearing much. There's not much there. Now you're probably starting to hear the bass come in a little bit and maybe a little bit of the kick. Depends on what you have for speakers. All right, we're at 60 right now. Here's 90, 100. Here. Let's delete that one. Let's grab this one. Let's change this. Let's make it narrow. Alright, here we go. Alright, so here's 30, 40, 50. Here's 80. You're starting to hear the bass more. Now we're at 120, and you're starting to get some kind of drums. Here at 250, we're starting to hear the horns a little. Now we're at 500. It's the body of a lot of the instruments. 1,000. 2,000. You can see why this kind of area is where they're going to target the phone, because this is where it's most clear. The whole overall, if we were just to play one band, there's 3,500. Makes me cringe a little. So there's 5,000. I don't like it. 8. Here's 10. Now we're playing up at 15K, so it's just the frizzy bits. It's also distorting because I'm pushing it too loud, but you get the point. So now we've listened to kind of what each of the frequency, I don't want to call them bands because in that respect they don't really exist. They're measured in octaves. But as we sweep along the frequency bands here, you can hear it's just lows down here, mids over here, and highs over here. So if you have a mixing board that has 3 controls on it, it's analogous to just having 3 points on one of these. I got to change them all too. I'll discuss the curves in a bit, but let me change these all so they're the same. All right. So if you have just a normal parametric EQ like on a mixing board, then you probably have low, right? And this is probably wide like that, the Q of it. And then you have your mids, which is also probably wide like that. And then you have your highs, which is also wide. This is probably, let's even them out a little bit like so. So as you're controlling your lows, it's the same thing as doing what I'm doing on this type of EQ with my mouse. So if you turn down the lows, then this is happening. If you turn them up, then you're doing this. And if you turn up the lows, you're probably going to hear more of what we heard in this area, which is going to be the kick drum and the bass, right? So if you're trying to bring the kick drum and the bass out, maybe boosting up here makes sense. Maybe cutting everywhere else makes sense. Either way, it kind of achieves the same thing. Doesn't matter that much. But what I want you to see is that it's 3 points. I mean, this looks cool with all the waves and stuff, but it's not all that complicated. When we play the music, we can see what this particular curve does. Let me freeze it. Okay, so see, this is showing me that the signal now is the brighter one, and the one kind of behind it, this is what the signal was before I applied these sweeping EQ curves. You can see that I've turned up areas and I've turned down areas. Here we are turning up. Sorry, I told you it backwards. The one behind is the original signal. So we're turning up here. You can see this wasn't there in the original signal, and then we're turning down these frequencies now. This is where that was, and this is where it is now. And then we're boosting the high frequencies as well, and that's what it sounds like. Now I'm going to turn it on and off so you can just hear the result of, this isn't a curve, this is arbitrary, the curves we're making. I just want you to hear what it's doing. So it's very dramatic. These are very dramatic curves that we drew here, but you can, this particular EQ can enable me to do that without it sounding too terrible. Whoa! Fix my chair. God damn it. God damn it. God damn it. All right. Stupid wheelie chair. All right. Okay, we're back in action. So let's get rid of these curves, and let's talk a little bit more about EQ in general. I want to run through the EQ sweep one more time, and we're going to do that sweep, but now we'll do it the opposite way, where I'm going to cut the frequency. Not that kind of curve. We want this. Whoop. We want this to be a bell. Whoop. Okay. Make it fairly wide, and I'm going to cut the frequency instead of boosting it, so you can hear what taking away a particular portion of the frequency spectrum is going to sound like. There goes the bass and the kick. There go the horns, kinda. They get much different. Oh, there they go. Now they're just not even. This is 3.5K. This is what happens if we remove 3.5K. So I want to call out, if we remove 3.5K, everything sounds kind of muffled and undefined. You can't really tell where things begin and end, because that's the portion where we start to discern the difference in sounds. Okay, cool. So now you've heard if I boost frequency and just sweep it across the whole spectrum, or if I cut it across the whole spectrum. And things that are important for you to keep in mind are that this type of EQ and the type of EQ that you see in your mixer with the knobs, they do the same thing in pretty much the same way, with the difference being I have a lot more control over like the width of each frequency band that I use. With a tool like this, I can make it very, very narrow and surgical and just take out one offensive frequency if I needed to, and you don't have that kind of control on a mixing board. But that's okay. It's fine. You know, they're here for the purposes that we need them for when we need them. All right. Now let's talk about some practical purposes of EQ. Now, you can kind of think of EQ in two different stages or two different methods. There's subtractive EQ when you're taking something away from the signal, and then there's additive EQ when you're adding something to the signal. Now, in general, if you're gonna make a change to the EQ of a sound, if you take frequencies away, cut the frequencies away, it sounds more natural. It sounds less affected than if you were to boost those same frequencies. So when we add frequencies, it sounds a little more fake than when we remove them. So a lot of mixing engineers will break it into stages, and the first stage is called subtractive EQ. So we're listening to the signal, and we're listening for things in it that are problems, that bother us, and then we're removing them first. We're not thinking about adding frequencies to sweeten the tone or fill anything out. We're just like, something's kind of hurting my ear in this sound. This guitar is kind of piercy. So we might take the EQ and look for wherever that piercy sound is with our dials or with our button here, like this. And we just kind of sweep along and look for it until we can reduce that sound. Right, that's reductive EQ or subtractive EQ. And that's what I recommend that you start out doing. That's what I do primarily. I cut way more stuff than I boost. And the biggest cut of all, I think, is in the low end. So I just want to talk about this for a second. Let's record another signal of just me talking, because I personally love hearing it. So let's make a new track here. And then we'll turn off the music for a second. And then we'll turn off the loop this time, because you're not going to fool me twice. And then we're going to hit record, and I'll say something witty and clever. Here we are laying down some audio on this Japanese hard drive. It used to be tape, but now tape is expensive and loud and I don't want to deal with it. So now we're just recording to a solid state hard drive that doesn't have any moving parts or make any noise in any way whatsoever. And I can write 1200 megabytes per second to it. It's pretty fantastic. All right, good enough. So let's take a look at what that looks like in the frequency analyzer of this EQ. So the frequency thing here, the thing that's actually showing me the display, that's called a frequency analyzer, and it's a function of this particular EQ. It's not part of an EQ. It doesn't do anything with the signal. It's just kind of a convenience thing. So let's see what this looks like. Let's loop that. Here we are laying down some audio on this Japanese hard drive. It used to be tape, but so let's take a look at what's going on here. So we see a bunch of information down here in this low end that's at like 20 hertz, 50 hertz, 100 hertz. But the thing is, down at 20 hertz, I can't even hear that. Like that's too low for human hearing even. So this is just noise at that point. Now at 50 hertz, we can hear that, and there could be some useful information in this. But my voice doesn't go down that low. No male voice goes down that low, I don't think. That's really low. So let's listen. Let's cut off all the frequencies and hear where my voice actually starts. So let's listen to this, and we'll just use a filter, and we'll filter everything. And then we'll just pull it back until my voice starts. Let's play. Now tape is expensive and loud and I don't want to deal with it. So now we're just recording to a solid state hard drive that doesn't have any moving parts or make any noise. All right. So I'm using right now this particular shape of the curve that I'm using here. This is called a low pass filter. Usually you use a high pass filter, it goes the other way and you're filtering out this low end, but we're using this for demonstration. So we're using what's called a low pass filter. Now this means only low frequencies are able to pass this frequency. I mean this cutoff point. So as I move this, listen to what we hear. I'm at 60 hertz right now and I don't really hear anything. Now I'm at 100. Here at 250, I'm starting to hear some mumbly sounds, like if I were a zombie. Let me turn that up for you. So this is all that exists in the sound of my voice under 240. I sound like the Swedish Chef. Let's pull it back and see where it actually cuts off and we can't hear anything. I'm going to turn it up even more. I can hear some of the low end of my voice here at 116, but I have a subwoofer, so it's unlikely that if you're listening on your laptop speaker or on your cell phone or whatever, you probably don't hear anything. But there is information here that I want to keep. At 80, I still hear me, and then there we go. That's the end. At 67, I don't hear me at all anymore. So all this information here below 67 is completely irrelevant to my voice. It's just noise. And in one track, that's not that big a deal because most speakers aren't going to play it back anyway. But when we start recording audio, then we start layering track over track over track over track. And this adds up. And it starts getting louder and louder and louder. And what it results in is just a muddy mess of undefinable music. So a very, very common use of EQ is to just cut this bit off right at the source before it even goes to the disk. You're never going to use it. It's not helpful. It's only going to cause problems. So this is why you see what's called a high pass filter on microphones and stuff. That's usually a switch that you can turn on a high pass filter, and it looks like a shelf like this. That's what the icon looks like.
Here we are laying the...
This is reversed. Let me do what a mic one would look like. It's just the backwards. So let me change this from a high cut to a low cut. It doesn't have any moving parts or make any noise. So this is what that switch does, and a lot of times you'll see it on a mixer too. It has a picture that looks like this kind of sideways L. It's the shelf. Sometimes it's not as dramatic, but most of the time it's pretty dramatic, kind of like that. Right, so what we're going to do is, since we couldn't hear anything useful up to 60 hertz anyway, I'm just cutting all that out of the signal in any way whatsoever, and I can write 1200. And there we go. And let me turn this back down, because now we're listening to the whole thing. Megabytes per second to it. It's pretty fantastic. So this is a very common use of EQ, and I do it on almost every track that I'm going to record. Even when I put this particular video on YouTube, before I do that, I run it through one of those filters, and I cut out all that noisy bit, because all that's in there is like me hitting the microphone and trucks driving by and maybe the sound of the condenser of my air conditioner turning on, but it's not a clean part of the signal that I want to keep around. I cut that out as early as possible when I can. Right now I don't have an EQ in this chain, so I can't cut it out with any of these. I can cut it on this mic, and I think I do. Yeah, I actually already have it on here. So that's already reduced. But with the computer, as we can see, it's more precise, and I'm able to really just clean that out entirely, obliterate that low end that doesn't need to be there. The high pass filter is very important, and you're going to find that on every EQ. So let's look at the EQ that comes with Studio One, my DAW here, stock one. And then we're going to take another break real quick, because I'm running out of time. And we're going to do another thing with EQ here. I want to put a bunch of tracks here and show you how they all interact together. And then we're going to switch over to compressors, and then we're going to be good. So let's take a 15-minute break, and we'll come back and do a couple of quick examples. Cool. Enjoy. All right, here we go. We're back. So we're playing with EQ right now. What I'm doing is putting together a quick little loop that we can use as an example of just showing how all these tracks are going to interact with each other. I keep seeing my camera lose focus, which is annoying. And here we go. Let's just do it quick, because we're running out of time. I'm going to add some electronic drums to this real drum and bass track. Okay, so now I have a fake kick drum along with the real drums, and let's add a couple more tracks here. I want to have a bunch, so let's do that. So let's add another instance of that, and we'll load up some sounds. Just grab something random. Let's see That's groovy. All right, I'm going to put some hi-hats in. Which one was that? There it is. Here we go. why I'm not a drummer. Okay. Let's find a couple more sounds, and maybe not a drum sound, but some other interesting sounds. Let's grab a synthesizer. Yeah. All right, here we go. I want to count in this time, so I'm going to turn on the count in button, which is this one? No, that's punch in? No, one of these. This guy, I think it is. Pre-roll, auto punch, pre-count. I should probably play it in the key of the song. This is why I don't play the drums or the keys. Let's add one. I don't even know what key this is in. Let's find out. So I can ask Studio One. Let's have it detect, extract a chord track. There we go. It's in C. C minor. Which means I should, if I don't hit any of the, if I only play the white keys, then I should be good. Let's add something else. One more. I don't even know what this sounds like. Let's hear it first. Let's grab Just Dance. Oh, yeah. Oh, yeah. Here we go. So this isn't actually supposed to sound good. I'm just showing you. And then we're going to sing. Well, I'll listen to the loop to this and let me add one vocal track. And then we'll show you what I want to show you, and then we'll move on. Here we go. Let's add one more vocal track here. And here we go. I like chicken wings 'cause they are tasty. Chicken wings are the best. There we go. Here's our loop. I told Dr. Dre I was coming after. Focus on me. Here we go. I told Dr. Dre I was coming after him. Let's see you beat this. I like chicken wings 'cause they are tasty. Chicken wings are the best. I like chicken wings 'cause they are tasty. Chicken wings are the best. I like chicken wings 'cause they are... Okay, so here we go. We got a bunch of tracks. It's a sonic mess. There's all sorts of nonsense going on, and this is really obnoxious, the whole not focusing on me thing. I'm going to have to do something about that. Let me add an analyzer to all these tracks now so we can look at the EQ across them all at the same time. So I have one of those. It's made by, I think this is one dude, Melded Production. It's called M Multi-Analyzer. And let's just drag it over to each of our tracks. Well, bam. Here you go. One coming at you. For you. Boom. One more. I could have just selected all the tracks and applied it all at once, but that would have been too fancy. Alright, so now we have the multi-analyzer. Let's see what happens when I play. I like chicken wings 'cause they are tasty. Chicken wings are the best. So this is showing you a representation of all of the different frequency information from all the tracks as it's playing together. And you can start to see that there are areas in which there's a lot of overlap. So what we do here as sound engineers when we're recording lots of tracks together is we take all of the individual tracks and try to carve out the space where they're most important in our song. So those are some of the decisions we make. Like if you imagine a stage and a bunch of kids on the stage, every parent in the audience wants to be able to hear their child clearly, their violin player or their pianist or whatever it is. You need to make sure that each individual part can be heard and discerned with all the other ones playing. Now, when the EQ is like this and everything is bouncing all up against each other, that's difficult to do because this turns into a mess. So you could start playing with the volume of everything. That's one way to do it, and that's kind of what EQ is, right? If we're making EQ changes, we're adjusting the volume, but only on a specific targeted set of frequencies. So you could adjust the volume and just turn each person up when it's their time to shine, and that would be one way to do it. But another way is to just make space in each of these tracks for each of the other instruments. So I'm not going to go into mixing this track. We're going to have another whole 3-hour thing on just recording and mixing and stuff. So I just wanted you to see the problem and what EQ is used to why it exists. I mean, why we use it in sound so much, in recording specifically. So you would go through here and decide what's most important. In the low end, it's probably the kick. So you want to get the kick in the low end. You might want to take the EQ from all the other instruments that aren't the kick and just kind of dip them there. You don't have to cut all the frequencies of the low end out, but just give the kick a little room to shine so that it can come through everywhere else. And then overall, on the whole mix, you can see there's parts where like this has a lot of low end and not so much going on up here. So at the end of the day, we might just put one big boost here and like make the high frequencies higher, like here. Just everywhere from here on, make everything a little bit higher. We can do stuff like that. So that's cool. Now let's talk about compression a bit because we only got a half hour left. I'm going to mute all these, and let's just go to the vocal track about chicken wings, because I like that one. I think it's a winner. Muting everything but the chicken wing track. I like chicken wings because they are tasty. Chicken wings are the best. I like chicken wings because they are tasty. Chicken wings are the best. Okay. So let's think about what the compressor was originally intended for. Let's make this track just a bit bigger so we can look at it. So imagine this is a broadcast that we're trying to send over the radio, but the radio can only handle signals that come up to about where the crosshair is right now. So imagine that's the case. So if this were to happen, if this little spike, this little bit over the crosshairs, were to make it through out to the antenna, it would ruin the entire broadcast. So we put on a compressor here to turn this little bit down, and only this little bit, as much as we could. And then we found out a little bit later that we could control the dynamic range in other ways, like turning the quieter parts up or down, right? So maybe you see this bit over here towards the right where this is just noise on the line. Well, we can set, we call it a noise gate, but it's really a compressor. We can set that to say any noise that doesn't reach over a certain threshold, I want you to turn that down or off entirely. You see that a lot on guitar effects processors so that the guitars don't feed back when somebody's not playing a note. So noise gates is just another form of dynamic range control. It's a compressor. We talked about the functional controls of a standard compressor, and they are the threshold, the point at which we set for the sound to go over before we act. So if we set the threshold, you can't really see the scale, but this is -6 here. So if we set the threshold on our compressor to -6, this is this area where my crosshair is the area we're going to affect. Anything under this threshold would not be affected by the compressor. And let's pull up, I'm going to pull up the Fab Filter compressor too because it's pretty. Let's pull up a compressor. And we see we have on this one our 4 basic controls. Here's our threshold, and we're setting our threshold, say at -6 dB. It would attack only this piece over the threshold. Then we have our ratio, and that's set as a ratio, how many to 1. And it's set that way because when we do cross the threshold, it doesn't stop the signal entirely. It does still allow some of the signal to pass through that threshold and get louder, but it does it at a ratio. So if you have the compressor set to 2 to 1, once you pass the threshold, the machine will make it such that the volume that goes over the threshold, it takes 2 decibels to turn it up by 1. So it takes double the energy to turn it up by half as much. And then that increases as you increase the ratio. So then you could go to 4 to 1, and then you're turning it down. It's not really turning it down, it's just not allowing it to come up. That's sort of more how they work. So let's just play the signal through this compressor and see what it does. Chicken wings. Set it all to normal. Let me set this to 1 to 1. So I'm going to set this to a 1 to 1 ratio here. That means the signal is going to pass through this compressor, but it's not actually going to do anything because we have a 1 to 1 ratio. For every bit of amplitude that crosses over the threshold, we get 1 in return, 1 to 1. Let's see. I like chicken wings because they are tasty. Chicken wings are the best. So this particular compressor is showing us in a couple of different ways where the signal is. You can see the little green line that's going around this bar. That's showing us an indication of where the threshold is. I like chicken wings because they are tasty. So right now it's at minus 18. So minus 18 on our scale here would be down, like here where the crosshair is. So anything over this point is what the compressor is working on as it's set right now. And right now I'm not having it do anything when it crosses over the threshold. The best. I like chicken wings because they... All right, let's engage the ratio a little. We'll say 2 to 1. They are tasty. Chicken wings are the best. Stop, stop, stop. I want to make it stop. Make it stop. Come back. They are tasty. Chicken wings are the best. Will that work? I like chicken wings because they are tasty. Here we go. All right, so now it's playing, but I just turned it down so you can't hear it. We can just see what it's doing. So we have this set at minus 18 dB, which is about right here on our scale. And now, whenever the signal crosses that, you can actually see the crosshairs on this threshold. It's being turned down. It's not being turned down. It's only allowing the bits that go over. You can see the green that goes over this line. It's only allowing those to come up. Right now we have 2 to 1. So it takes 2 decibels to turn it up by 1, which is effectively turning it down. Right? And now this is just an easier way to look at it. You can see the gain reduction meter. This meter in red is showing us how much the compressor is working, and this line, this red line, is showing us what it's doing. So you can see every time that the compressor clamps down and turns something down, and then you can also see how quickly it recovers. So I hope that you can understand this relationship between the threshold and the ratio. Let's move the threshold a little bit so that it triggers different things. So if I raise this up to where not as many things hit it, it does a lot less work. Right, because now this we're setting the threshold much higher for the signal. So now it's only attacking these bits at the very top. Now, my chair can't roll on its little rolly base, and it's super annoying. Now, there's a couple of other controls here that you need to understand, and they're attack and release. Now, when we're turning down the signal, so we've crossed the threshold and we've decided that we're going to turn down the signal. Let's, just for an example, let's turn it down as much as we can. So when we cross the threshold, we're going to turn it down by 100 to 1, which is pretty much what we would call a limiter. It's like nothing's passing the threshold. So let's turn that on just for the example. Right, so now we have this set to a limiter, and it's being aggressive at our threshold. Let me turn that down more so it works a little harder. And let me fix this loop so we don't have that dead space. Cool. All right, so now we can see we're turning down the signal by quite a lot. This is like 9 decibels every time I say anything there. And that has a couple of different effects. It brings the overall volume down some, right? And it brings the louder bits of my voice closer to the quieter bits, so it evens out my speech more. So you hear when I trail off, the compressor helps to even that out, and that's a good purpose for it. So we have 2 other controls here, though. attack and release, and these can be confusing. And as we saw going through the analog compressors, not all compressors show you what they are, but all compressors react in the same in they exist. Attack and release are an inherent component of all compression. So the attack is how fast the compressor starts working. Let's I don't really like this signal. Let's look at just a kick drum loop. Let me see if I can find a loop of a kick drum, just because it's a little more consistent, right? Loops, drums. Let's grab kick snare. Well, that's loud. All right, let's grab this one. And then let's look at that with the compressor on, and it should be muted, so you shouldn't be hearing it. All right. Now this is just a little easier to see what it's doing. Every time the kick engages, it turns the kick down because the kick is crossing the threshold. And as we move the threshold, we will see more or less gain reduction as the signal crosses over. This is really loud signal to start with, so let's fix our loop and turn that down. Turn this down a bit. All right. Woo, sorry about that. So as I move the threshold down, you can see more and more gain reduction is applied until there's, a ton. And the more gain reduction you apply, the more distortion happens, and that can be pleasant distortion or it can be unpleasant distortion. And the sound of the distortion is dependent on the components or the modeling inside the compressor. But we're talking about attack and release. Right now, we have our attack here set to 0.25 milliseconds. That's pretty fast. And now we can start moving this and see what happens to the signal as I raise the length of the attack here. Let me make it pretty dramatic. All right, and let me stop this. You can't stop it. It has to keep playing. But look at this. Look at how this line is turning down the music now. A lot of the beginning of the sound is passing through the compressor before the compressor really starts to turn the signal down. And as I move that to faster, look how fast it reacts. It turns the signal down as soon as the signal happens. Now, this is useful to us in a couple of different ways. One of them is if you're trying to do that brick wall limiting type thing where you're trying to protect a signal from getting too loud because it might clip a piece of gear, you probably want a pretty fast attack because you don't want any of these transient bits to sneak through the compressor. But if you're using this for musical reasons, this gives you control over the placement of different sounds in a mix. Because if you think about, drums are a good example. If you think about a snare, when you hit the snare, it's a really loud, really fast sound that happens, and then there's another sound after it that's like the body and the resonance of the snare drum. Right? So the waveform is a big snap, followed by a trail off of the body. Right? You can see it in this waveform. Well, if you were to use a compressor and compress that transient bit, the first part of the smack, well, it's going to make the drum sound stand out less. It's going to move the sound of the snare drum back in the mix. It won't be as prevalent. But if you want to accentuate that, then you could use a compressor and you can move the attack so that it's kind of slower to respond. And now you can see what it's doing here is it's accentuating that attack bit, and then it's pressing down the other bit so that it and the sustain become more consistent, more compressed together. So now you still hear the snap, and then you also hear the nice fat compressed sustain, and that can really fatten up the sound of your snare drum. So this is why you're using the attack. It's for a couple different reasons. One's just for the speed to make sure nothing can get through if you don't want it to get through, and then another is to control the placement of something in a mix. If you want something to really pop out, then if the transient of it pops out, it'll pop out like a snare drum or a vocal track or something like that. But if you want to tame something down and move it back, it's annoying, a cowbell or something like that, then you might want to squash that transient down with a really fast attack time. And release is very similar to that in that this is how fast the compressor responds. So right now we have it set to somewhere in the middle. Let's make it really fast. Right now it's a lot more jittery. It's letting go and compressing a little bit more. And let me turn that sound back on for you for a second. I know it's going to be annoying. Here it is. Now let's turn it off. Off, on. So it can be confusing if you're using your eyes to try and gauge with a meter like this what it's doing. So you really want to listen with your ears to what it's doing to the transient sound. In this, just where it's set right now with this ratio, I hear this a lot, and it's kind of making a pumping kind of sound. It's letting a bit of that transient thud of the kick drum through, and then it's compressing really heavily on the rest of the sound, and I hear that as a sort of a pump sound. Now we can adjust how much of that I hear, right? You can use that for creative effect. You can make your drums sound more bouncy and more like alive with the compressor because it's helping you make the sound pump the way that you want the sound to pump. It can also deaden the sound. You need to be able to hear. That's what you're listening for. You're listening for the life and the bounce that it brings sometimes when you're using a compressor. And that is controlled by the attack and release, how fast they are. And that's a lot of why in the old analog days people chose the different hardware compressors, is because they just had different attack and release characteristics. And when you put different types of music through them, sometimes it made them bounce, sometimes it toned them out, sometimes it just had that sound that they needed, and it gave an additional level of musicality to things, because it also distorted a lot and added some noise that was harmonic and pleasant to our ears, and it adds this warmth and richness that we associate with great music. Really today, if we didn't have any of that for the last 30 or 40 years, we'd be like, this is noisy. This music is noisy and distorted, right? It sounds wrong. It sounds broken. But we grew up with it. We loved that, and it was very musical to us, and we try to replicate it as best we can today. So that's basically how a compressor works. You have 4 controls: the threshold. Again, this is when does the compressor start working. The ratio is how much gain reduction do you want to apply. Then we have the attack. It's how fast do you want to clamp down on the sound. And then you have the release, and that's how fast you want the sound to come back up to no compression at all. And you play with the attack and release times on these to get the result that you want. Sometimes you want to hear the compression. You're using it to help make something stand out. And sometimes you're using the compression to make something fit in. And in those instances, you don't want to hear the compression. You want it to sound very natural, and you want it to, you don't want people to know there's an effect there, right? You have a lot of leeway for it with speech. If you're doing podcasts and stuff, you can kind of really smash your vocal and get away with that, because that's really what they did with the old tools, is they just smashed the vocal so that everything was of a similar volume, and then they pushed that out as loud as they could without overmodulating the antenna. So they had some controls in place to make sure that they never got a little too loud, nobody got too high and flipped the switch the wrong way. And they built these tools. And then sound engineers after that came and took them and started being like, wow, this compressor turns down the sound really fast, or this compressor turns down the sound really slow. This one makes my voice sound warmer, and this one makes my voice sound meaner or more aggressive, like a 80s rock kind of tone, right? those are some of the characteristics of these tools. Now, you also we looked at the beginning of this workshop here. We did the sidechain compression here, where we used my vocal track to control the volume of the music behind it. That's a popular thing to do. So if you missed that part at the beginning of our workshop here, we set up this in a sidechain configuration, and we sent my spoken word track to the compressor and had the compressor turn down the music behind us. So we set up audio ducking. And we're going to go into audio ducking and mixing and recording in much greater detail in the coming weeks. I just wanted to give you the overview here of what these tools are and where they came from. So hopefully they're a little less scary, because there's not really that much going on. Even if you look at a big mixer console with 30 channels or whatever and all those knobs, it's really just lines of a couple of knobs, right? The EQs, there's usually 3 knobs, high, mid, and low. And then some mixers might even have a compressor on them, or your guitar amps, and they're going to have similar controls like this. They might not be knobs. It might be in an electronic or in a like an LED type interface or whatever it is. But you're going to have these similar controls, and this is why. So cool. And coming up next week, I think let's take a look at our slides and see where we're going, because I'm losing track. We just did all about microphones, and then we did compression. We're going to have to do some reverb and delay talk, and then we're going to have to talk about recording. I think maybe we'll do reverb and delay next week, and then after that we're going to start doing digital audio workstations and recording a song, and then we'll create some material to use to demonstrate mixing and mastering. So there's quite a few more of these to go before we get to the end, and let me know in the comments or whatever if there's any part of this that should stand out more than the others. Don't forget, after these live performances, I clean these up and I put them on YouTube. So if you're not following my YouTube channel, that's the place to be. I put a bunch of stuff up there. Also, stick around, because Laura's painting. Laura Senandela is painting. She's working on her show. It's coming out great. She's doing, I think, 3 hours of painting something awesome today, and it's worth checking out if you're hanging out on your Saturday afternoon. Check out Laura on the Blackstone Valley Art Association page and her own page, and when I sign off, she'll be about signing on, so get yourself a drink, some hot chocolate, and we'll come back next week and talk about reverb and delay and the fun stuff. All right, thanks for spending another Saturday morning with me. It's been fun. I will catch you next week.